Okay, so all of that has been discussing discrete probability densities. And a lot of the variables that you encounter in the real world are not discrete, but they are actually continuous. So, for example, age, we were looking at in the previous slide. Instead of measuring age as a kind of year, you're measuring it actually continuously. Like somebody can be 55 years old, but they can also be 24.2 years old. And we're treating this as a continuous variable, and it's in some infinite population where I can't physically count. What is then the density function? So now, if you look at the x-axis, so let's say this is age, right, between 0 and 100 or something like that, at any value of x, so not just 1 and 2 and 3, but at x equals 1/2, or at x equals square root of 2, or x equals pi. Somebody, could be pi years old. At some point in time, you were exactly pi years old. So now this density has a value at each of those values, so you can trace out the curve of the density. But unlike the case with discrete variables, the value of the density at a given value does not represent the probability that the random variable takes that value little x. And why is that? So let's look at this problem. Again, I encourage you to pause and read this and try to figure this out for yourself before moving on. But I'm telling you, let's say that the probability of finding a person of any given height between 5 and 6 feet in some population is some tiny number. So what I mean is not the probability of being between 5 and 6 feet. What I mean is this here. So for any number between 5 and 6 feet, the probability of somebody being that height exactly is this number, like 0.001. So for example, the height of being the probability that you are 5.5 feet tall exactly is 0.001, right? The probability of you being 5.5 feet tall plus some tiny fraction of an inch is also 0.001, and so on and so forth. The probability of being 5 plus square root 2 or whatever is also that number. So I could keep adding bullets here for every possible number between 5 and 6. My question is, why is that impossible? And what if I make this number, instead of 0.001, I made it, some arbitrarily tiny number? Why is that still impossible? So the answer is that there are an infinite number of numbers between 5 and 6, and I have to account for all of them. So if I'm adding up I know that basically the sum of the probabilities has to be 1. So if these probabilities are all some finite number, no matter how small it is, but I have an infinite number of them, then these probabilities have to sum to infinity, right? I'm adding up, no matter how small the thing is I'm adding up, if I'm adding up an infinite number of it, it's going to be greater than 1. So that's not possible, right? So what this implies, which is interesting, is that if and somewhat counterintuitive, is that if you have a continuous random variable, the probability that that variable takes any particular value is typically exactly 0. Okay, so that may seem counterintuitive because obviously everybody has a height, and everybody there is some distribution of heights, right? It's not totally arbitrary, but the chance of finding someone in all of human history who is exactly 5 feet tall, not 5 feet plus a millimeter, not 5 feet plus 1 nanometer, exactly 5 feet, out of everyone in all of human history, the number of people who are exactly 5 feet divided by the total size of the population is exactly 0. Okay, that's what this says. However, you still have this concept of a density, because relatively speaking, are people more likely to be close to 5 feet, or are they more likely to be close to 100 feet? Clearly, the answer should be that they're more likely to be closer to 5 feet than 100 feet tall. And so there still is some notion of relative likelihood, even though the absolute probabilities at each of these points is exactly 0. And that's what a continuous density is. The values are not absolute probabilities; they're relative probabilities, where it's relative to other values. That is a bit hand wavy, admittedly, but if you don't really dive into the measure theoretic background of probability or have some calculus background, this is not really that. It's not going to be that accessible. But I do recommend, there's a YouTube channel called 3 Blue 1 Brown, or often abbreviated to 3B 1B, and that guy has a video about densities, which is very similar to what I just talked about here. But if this is something that you're interested in and you want to learn more, even if you don't have that kind of calculus background, I recommend checking out that video. Or again, you can kind of work with ChatGPT to try to deepen your understanding a bit. So another way to think about it is that you can imagine your population data set, and again, your population is infinitely large, and you can think about what would happen if I took increasing samples and then made a histogram from those samples, where as I increase the size of the sample, I'm also shrinking the size of the buckets that I'm binning people in. Because when you make a histogram, right, you chop up your values on the x-axis into these different buckets, right? Like age between 0 and 10, age between 10 and 20, so on and so forth. So I have buckets of a particular size. So if I take a sample of size 100, I'm saying maybe the buckets are bins of size 10 years. Then when I take a sample of 1,000, I shrink the buckets down to, let's say 2 years. And then with 10,000, I shrink the buckets down to, a tenth of a year, and so on and so forth. So if I do that, and I keep going forever, and I take the limit of what that shape looks like, that is the continuous probability density. Now, why is that useful? Why do we care about having the density and whatnot? Well, because for continuous variables, it works the same way as for discrete variables, in that if I have the density function, I don't need the population data set in order to calculate probabilities. Now, that's really nice, because if I have an infinite population with continuous variables, I couldn't even make up a population data set, because I couldn't fit it in memory because it's infinitely large. And so really all we can work with is the density function. Now for a discrete random variable, we have this way of calculating the probability. For a continuous random variable, it's very, very similar, except that now instead of adding up the values, we have to integrate them. The integral is basically just a continuous sum, so I'm summing over x in for every possible value between 0 and 5, and I don't mean integers 1, 2, 3, but I mean 0, 0.00001, 0.0002, all of the possible values. I'm adding up the value of the density times some tiny increment, which is the distance between two values. So again, this is something from calculus. If you haven't seen calculus or taken calculus, it's not going to make sense to you. That's totally fine. Not important. I'm just showing you the notation so that if you see this, you're not totally afraid, because this is really just a version of this for continuous data. And the graphical intuition is the same. So for discrete variables, if you're asking about summing up the value of the density, the value of the density is kind of the height of this orange bar at each point x. So if I sum up for x in some particular set of values, so let's say between here and here, the sum of the density is just adding together the heights of these pink bars. When I'm taking the integral is to correspond to the area under this density curve between two values, or above a particular set x. So here, this set I'm giving by the script x with this kind of gray zone here. And the area under the curve above that gray zone is the pink here. And so what I'm trying to graphically convey is that this formula here and this formula here both are doing the same thing. They're just area under a curve, so to speak. It's just that this curve is not really a curve. It's just kind of like a series of points. but they're really doing the same thing. So to calculate probabilities, if you have a density, you just need the area under the curve, under that density, at the values whose probability you're interested in. And the reason this works is the same. It's just that you're counting, instead of counting in a population data set and dividing by the total, you're counting by groups. So first counting all the people who have a particular value, then counting all the people who have a different value, and adding those up. So if you're confused by that, don't worry. I'm firmly of the opinion that practically all intuition statistics can be gleaned from considering a finite but possibly very large population with discrete variables. So if you have age, just think of age as discrete, counted in days, right? There's a lot of days in a year, and there's several years in a lifetime, so there's a lot of possible values that age could take, but it's still a finite number, and so you can still conceptually think of it as a density, a mass function with in a table. So if you ever get lost in kind of problems thinking about density, blah blah blah, whatever, just pretend you're in that setting, and all the formulas, all the definitions will come down to very intuitive, just different ways of counting, right? And then once you have that, just extend that, just pretend it works in the case when you have infinite populations and continuous densities, and it basically always does. All right, so another conceptual question. Again, not relevant to practice, but we're thinking about these things to deepen our intuition. So the question is, what is the total area under the curve for any density function of a continuous variable? So the answer is pretty straightforward. It's 1. And the reason it's 1 is because we're asking about what is this total area under the curve here, which is analogous to here asking about what is the sum over all values of the density function. And as we talked about, that has to be 1 because you're kind of asking about, if you want to look at this top view instead, the area under the total curve corresponds to the probability that x takes any value. And what's the probability that x takes any value? It's 1. X has to take a value. We have a measurement for everybody. So that has to be 1. So reminder to beat this to death. All of this is imaginary. We never have population data. You never know the true distribution. These are just tools. And we need to understand these tools so that we can understand and discuss the assumptions that are inherent in the kinds of methods that we use when we do real data analysis. But you're never going to go out in the world and have a population data set. You're never going to go out in the world and have an actual density function. So these things are just abstractions that help us think. Just the same way that the number 2, you're never going to see an actual number 2, but of course we use number 2, we use the number 5 all the time. But the number itself is just an abstraction, a tool to help us think.